In this video, we're going to look at section 8.2 about the graphs of the polar functions. To get started, let's look at the connection between the graph in rectangular xy coordinates and polar r theta coordinates. Here we're going to look at y equals 2 cosine x and r equals 2 cosine theta. Now in this case, what's going to happen is the values of x will correspond to the values of theta in the polar coordinates, and the values of y we can take as corresponding to the values of r in polar coordinates. So in this case, the coordinate 0, 2 will relate to the point 2, 0 in the graph of the polar coordinates. And we'll follow along here with the angles, and as we do, we'll notice how the value of r will shrink until it gets to 0. What this will do is complete the top of the shape in the polar graph. So looking at the polar graph, notice how at pi over 6, it has a point for r, and then that point comes in closer to the origin at pi over 3 until it gets all the way down to 0 at the angle of pi over 2. And this also corresponds to the point pi over 2, 0 in the rectangular graph. So we can follow the rectangular graph as the values of r shrink from 2 all the way to 0, and relate that to the shape of the curve in the polar graph as it starts from r equals 2 and shrinks down to r equals 0 as the angle varies between 0 and pi over 2. And this cycle will continue as we follow along the rectangular graph, and that creates the bottom of the shape in the polar graph. So it'll go down to -2 at pi, to 3 pi over 2, and then it'll go back to 0 again, and then it goes all the way to 2 at the angle of 2 pi. So 2, 2 pi will actually complete the cycle all the way around the shape that we see in polar coordinates, and will complete the graph in polar coordinates. Now this actually makes the shape of a circle, and is in general going to relate to the equation of a circle in polar coordinates. In general, the orientation and size of our circles in polar coordinates will depend on which trig function there is and the value of a. So for instance, r equals a cosine theta will create the graph of a circle in polar coordinates, and if a is greater than 0, that circle will show up on the left side, and the distance away from the origin to the furthest part out on its diameter will be a. And so the circle is more or less located on the left side of what we would normally consider the y-axis in rectangular coordinates, and is centered along the x-axis. If the value of a is less than 0, then instead of being on the right side, it'll be located over on the left side of what we normally consider the y-axis in rectangular coordinates. Still, the distance away from the origin, ultimately the diameter of the circle, will be determined by the value of a. The orientation will change if the equation has sine theta instead of cosine theta. So if a is greater than 0, it'll actually be located on the upper half or above the x-axis if we're thinking in terms of rectangular coordinates. And if a is less than 0, then the circle will be located down below, and still the diameter and the distance away from the origin would be determined by the value of a. We'll take a look at some more graphs in their rectangular and polar forms. Here, let's look at the y equals 1 plus cosine x in rectangular and r equals 1 plus cosine theta in polar. And so this one starts at 2, 0 in polar form. And if we follow the values from the rectangular graph, the polar graph will go from 2, 0 to 1.5, pi over 3. And as that angle increases to pi over 2, the value of r will shrink to 1. And we can follow along as it shrinks all the way from 1 down to 0 at 0, pi. And then from there, it's going to go back out again. As we can tell in the rectangular graph, it's going to get bigger. And so from 3 pi over 2, 1 comma 3 pi over 2, it will have reached 1. And then it will swing back out to 1.5. And then complete the entire cycle in the polar graph at 2 comma 2 pi. This particular polar graph has a name called a cardioid. Another somewhat similar type of graph looks like this one. It goes y equals 2 minus sine x in rectangular and r equals 2 minus sine theta in polar. And so we can follow along here as the polar graph starts from 2 comma 0, then goes through 1.5 comma pi over 6, and then to 1 comma pi over 2, 1.5 comma 5 pi over 6, 2 comma pi, and then it goes all the way out as it reaches 3 comma 3 pi over 2, and then completes the cycle at 2 comma 2 pi. This particular graph is called a limmason. It's sort of like a circle with one part of it's kind of flattened out a little bit. And so we see cardioids and limmasons in general in polar form when we have these particular types of equations, such as r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta, where a and b are both greater than 0. And the orientation, much like it was for a circle, will depend on which trigonometric function, the sine or the cosine, and the sign of b. And so the different shapes we might see in polar graphs with these particular types of equations is a limmason with an inner loop when a is less than b, a cardioid when a is equal to b, a dimpled limmason when a is greater than b, and a convex limmason when a is greater than or equal to 2b. Another interesting graph here with some neat features to it has a rectangular form y equals cosine 2x, in the polar form r equals cosine 2 theta. And if we follow along the points in the rectangular graph and relate them to the polar form in the polar graph, we actually have a period which is shorter than the other graphs because of the 2x or 2 theta. So we actually can go through 2 complete periods here as we go from 0 to 2 pi. And we'll see how that makes the graph happen in this case. So starting from the point 1 comma 0 in polar form, the value of r will shrink until it gets to 0. And that relates to the pi over 4 comma 0 in the rectangular graph. And then it's going to go all the way to negative 1 as it goes down. And in polar form, the negative 1 comma pi over 2 is actually going to be down here at the bottom. Due to the fact that r is negative, that's where we would have to put it. And then the values will go from 0 back all the way up to 1 again. So it passes through 0, and then value of r goes back to 1 with 1 comma pi in the polar graph. And repeats the cycle over again, going to 0 down to negative 1, where the polar form coordinate would look like negative 1 comma 3 pi over 2. And that's actually going to be up here on the top due to the fact, again, that r is negative. But it completes the cycle over again by going through 0 all the way up to 1 again. And so in polar form, that'd be 1 comma 2 pi. And so that completes the cycle by getting back to the point where we started. And so once we do that, we've completed the full graph in polar form and traced our way through all the points. Now this particular graph will have like 4 different leaves or petals to it almost, because the graph goes to 1 in 4 different places, 1 to negative 1 to 1 to negative 1 back to 1 again. So it makes that cycle and makes 4 different points that go out to 1. And so we call this a 4-leaf rose. So it turns out we can have a lot of different polar graphs that look like this with different configurations, with r equals a sine n theta or r equals a cosine n theta. And the number of n that shows up in front of theta will determine the number of leaves. There will be n leaves if n is odd, and there will be 2 n leaves if n is even. So for instance, r equals a cosine 2 theta would be a 4-leaf rose like we saw. Cosine 3 theta would create a 3-leaf rows, 4 theta would create a 8-leaf rows, and 5 theta would create a 5-leaf rows. And the number a out in front is really just going to determine how big the graph will be. If a is bigger, then the petals will be bigger. If a is smaller, then it will turn into a smaller graph. In general, there are a lot of different interesting graphs of polar form, and we can see several here. We've looked at the limacons and the roses. There's also the circle equations up above. Spiral is another interesting one. And then the ones at the bottom, kind of like almost like infinity shapes. And there are equations for those as well in polar form. Now we can tell beforehand if a polar graph will have particular types of symmetry. And there are actually 3 types of symmetry in polar form. Symmetry about the polar axis, symmetry about the line theta equals pi over 2, or symmetry about the pole/origin. And the polar axis symmetry, which would correspond in rectangular form to x-axis symmetry, we can determine this by replacing theta with negative theta. If an equivalent equation results, then the graph is symmetric with respect to the polar axis. We can check for symmetry about the line theta equals pi over 2, which corresponds to the y-axis in rectangular form, by replacing the r comma theta with negative r comma negative theta. If an equivalent equation results, then the graph is symmetric with respect to theta equals pi over 2. And then we can check for symmetry with respect to the pole or origin by replacing r with negative r. If an equivalent equation results, then the graph is symmetric with respect to the pole. So a few examples of this here. R equals cosine 2 theta. We can check for symmetry by replacing theta with negative theta. And that would make it look like r equals cosine 2 negative theta. Or in other words, r equals cosine of negative 2 theta. Since cosine is even, however, cosine of negative 2 theta is the same as cosine of positive 2 theta. So as a result, by putting a negative theta there, the equation still would be r equals cosine 2 theta. What this tells us is the equation did not change after replacing theta with negative theta. And as a result, we can know beforehand that this thing will have polar axis symmetry. On the other hand, if we replace r theta with negative r comma negative theta, then the equation would look like negative r equals cosine 2 times negative theta, or r equals negative cosine of negative 2 theta. This is what happens if I solve for r, move that negative from the r over to the other side. But because cosine is still even, we can take that negative 2 theta and make it positive 2 theta. So r equals negative cosine of 2 theta. This, however, is not the same equation with these two variables changed. So after replacing r theta with negative r negative theta, the equation changed, and so we say it's inconclusive if the graph will actually have symmetry about theta equals pi over 2. The last check would be to replace just the r with negative r. That would make it look like negative r equals cosine 2 theta. And the only thing I'll do here is solve for r and make it r equals negative cosine 2 theta. Now as a result, this thing isn't going to go back to the way it was to get where we started. So the equation has changed with replacing r with negative r. So it's inconclusive in this case if it will have that type of symmetry, which here is symmetry about the pole. So if we go back to the graph of r equals cosine 2 theta, we can see that it actually does have, first off, polar axis symmetry, because the top and bottom are mirror images. It does also have symmetry about theta equals pi over 2, because the left and right sides are also mirror images. It also has symmetry about the pole, because if we go between 2 points on either side, then they'll be equally distant away from the pole in the middle. So it is symmetric about the pole. One more example, r equals 2 minus sine theta. I'll go through the steps of checking symmetry in this particular graph. So replacing theta with negative theta would look like r equals 2 minus sine negative theta. Now in this case we're dealing with sine, and sine is odd. So sine negative theta can be rewritten as negative sine of theta, putting the negative in the front of the sine. But that makes double negatives, so it would be r equals 2 plus sine theta. As a result, the equation has changed after replacing theta with negative theta, and so it's inconclusive if this thing has polar axis symmetry. If I replace r theta with negative r negative theta, it would look like negative r equals 2 minus sine negative theta, which would be the same as negative r equals 2 minus negative sine theta, since sine is odd. And if I solve this for r, it would turn into r equals negative 2 minus sine theta, which is a different equation than the original one. So after replacing it, we have a different equation, and so it's inconclusive if it has symmetry about theta equals pi over 2. Now if we replace r with negative r, it would look like negative r equals 2 minus sine theta. Solving for r and make it look like r equals negative 2 plus sine theta. So since the equation has changed after replacing negative r, or r with negative r I should say, it's inconclusive if it has symmetry about the pole. Now looking at the graph, we can tell it has actual symmetry about theta equals pi over 2, since left and right sides are mirror images of each other. But it doesn't have any of the other kinds of symmetry. It doesn't have symmetry about the pole, nor does it have symmetry about the polar axis.